Welcome back to Spectre AI, where we break down quantum security one concept at a time. This is Spectre P. In today's video, we're taking BB84 to its final form: error correction and privacy amplification. Even after Alice and Bob sift their key, the raw bits still contain noise, mistakes, and potentially Eve's fingerprints. So how do we turn that imperfect key into a final secret key that's provably secure? That's exactly what we're covering today. If you enjoy these deep dive quantum security videos, make sure you subscribe. It helps us reach more learners around the world. Let's get into it. Even after Alice and Bob run the BB84 protocol, their raw key is never perfect. Real quantum channels introduce noise. Detectors misfire. Photons drift or arrive slightly out of alignment. So even when Alice and Bob choose the same basis, their bit values don't always match. What you're looking at here is completely normal. These errors happen even when Eve isn't attacking the system. Before Alice and Bob can generate a secure key, they first have to correct these mismatches, and they need to do it without ever revealing their actual bits. Once Alice and Bob finish basis sifting, they keep only the bits where they use the same basis. But matching bases doesn't guarantee matching bit values. Because of channel noise and detector imperfections, Alice's bit 1 might be received by Bob as a 0, or vice versa. So even after sifting, the shared key still contains errors. These remaining mismatches now need to be corrected. And that brings us to the error correction step of BB84. To correct the remaining errors in the sifted key, Alice and Bob start by splitting their bits into blocks. They don't reveal the bits themselves. Instead, they publicly compare the parity of each block. If the parities match, the block is clean. But if the parities differ, that means the block contains at least one error. From there, they use a binary search approach, cutting the block in half and comparing parities again until they pinpoint the exact bit that's wrong. Only the position of the error is revealed. The actual bit values stay private. This allows Alice and Bob to clean up their key without leaking any information to an eavesdropper. Before Alice and Bob can correct any errors, they need a simple way to summarize a whole block of bits without revealing the bits themselves. That summary is the parity, whether the number of ones in the block is even or odd. On the left, we set up the basic notation. Alice has her block of bits, Bob has his, and each bit is either a 0 or a 1. We'll use exclusive OR, shown in the truth table below, to compute the parity. XOR is perfect for this because it flips whenever the number of ones is odd. On the right, you can see the formal definition of parity for each block. Alice takes all her bits and reduces them to a single parity value. Bob does the same. They don't reveal their bits, only this one summary number. Using the example from earlier, the bottom line is simple. Alice ends up with one parity value, Bob ends up with another. And now they can compare those two numbers publicly without giving anything away. This sets the stage for the next step, using those parities to detect whether a block contains an error. Now that Alice and Bob each have a parity value for their block, the next question is simple. Do those two parities match? If the parities are the same, it means the block is clean. Or at worst, there were an even number of errors that canceled each other out, which is extremely unlikely in a low-noise quantum channel. But if the parities differ, that immediately tells them something important. There is at least one wrong bit somewhere in that block. They still don't know which bit it is. The parity only gives a yes or no answer. But that's enough information to start narrowing things down. Using the example from before, Alice's parity is 1 and Bob's is 0, so their block fails the check. That means there's definitely an error inside it, and now they move on to the next step. splitting the block and tracking down where that error actually lives. Once Alice and Bob know their block contains an error, the next question is, where is it? The trick they use is beautifully simple. They split the block into two halves. Alice computes the parity of her left half and her right half. Bob does the same for his halves. Just like before, they only share the parity values, never the bits themselves. Now here's the key idea. If the parities of the left halves match, then that side is clean. If they differ, the error must be on that side. Exactly one half will fail the parity check. That's the half containing the wrong bit. From there, they just repeat the process. They split the bad half again, compare the parities again, and follow the half where the mismatch occurs. This is literally binary search applied to an error position. Every round cuts the search space in half until there's only one bit left. And that bit is the error. Bob flips it, and the block is corrected without ever revealing any actual values. This is how BB84 aligns Alice's and Bob's keys while keeping Eve completely in the dark. Now, let's walk through an actual example to see how this plays out in practice. Here, Alice and Bob each have a block of 7 bits. At first glance, their blocks look the same. But as we already discovered, the parities don't match. That means there's definitely at least one error hiding in this block. So the first thing they do is split their block into two halves, a left half and a right half. Each of them computes the parity for those halves separately. On the left side of the slide, you can see the full block check confirming that something is wrong. And on the right side, after splitting into halves, you can see that the parities of the left halves match. That tells Alice and Bob that the left half is clean. There's no error there. This already cuts the problem in half. Instead of searching all 7 bits, they only have to focus on the right half of the block. Next, they'll repeat the same process again, splitting the right half and checking which side fails the parity test. Here we take a closer look at what happens after Alice and Bob split their block into two halves. On the left side of the slide, you can see that both of them have exactly the same bits in their left half. When they compute the parity, the results match, and that tells them the left side is clean. There's no need to investigate that half any further, but when they move to the right half, the picture changes. Alice has 3 zeros in that half, while Bob has 2 zeros and a 1. The moment they compute those parities, the mismatch jumps out immediately. A matching parity means this half is good. A mismatching parity means the error is somewhere in here. And in this example, the right half fails the parity test. So that's where the search continues. This step is powerful because it cuts the problem in half instantly. Instead of searching all 7 bits, Alice and Bob have now narrowed the error down to just 3. Now that Alice and Bob have narrowed the problem down to the right half, they repeat the exact same strategy. Split it again, check parities again, and see which side fails the test. On the left subhalf, both of them have the same 2 bits. When they compute the parity there, everything matches. So this subhalf is clean. No need to look at it further. But on the right subhalf, they immediately see a difference. Alice has a 0, Bob has a 1. The parities disagree, which tells them, with complete certainty, that this single bit is the source of the error. And here's the beauty of the whole method. By only comparing parities, they never reveal the actual values of their bits. All they learn is where the mistake is, not what the correct bit should be. Since Alice's version is the reference in this protocol, Bob simply flips his final bit from 1 to 0, and that one small change brings Bob's entire block into perfect agreement with Alice's. This is how BB84 cleans up noise in the key. A few rounds of parity checks, binary splits, and one final correction. and both parties end up with matching keys without ever exposing them to an eavesdropper. At this point, Alice and Bob have successfully corrected all the errors in their key. Their bits now match perfectly, but matching does not automatically mean secure. Even though Bob fixed his mistakes, Eve may still have learned something earlier in the exchange. Maybe she intercepted a few photons, or maybe channel noise gave her partial hints. Either way, even a tiny amount of information in the wrong hands weakens the final key. That's what we're showing here. Before error correction, Alice and Bob clearly disagreed. After error correction, their keys line up, but Eve may still know something. Not the whole key, not even most of it, but even knowing one bit is too much in cryptography. So, BB84 includes one more step, a final cleanup phase designed specifically to wipe out any information Eve could possibly have. That final step is called privacy amplification. Even after Alice and Bob fix all of their errors, there's still one problem left. Eve might still know something about the key. Maybe she intercepted a few photons earlier. Maybe channel noise gave her partial information. Even a single bit of knowledge reduces the key's security. Privacy amplification is the final step that removes that risk completely. Alice and Bob take their corrected key and run it through a shared hash function. This compresses the key into a shorter one. But the crucial part is what happens to Eve. Any partial knowledge she had becomes practically useless. Her uncertainty grows exponentially as the key shrinks. The end result is a smaller but provably secure shared key that Eve has essentially zero information about. And if you want a deeper dive into how privacy amplification works under the hood, we covered that in detail back in Video 10. Let's zoom out and look at the full picture of what we've built. BB84 starts with raw quantum data. Alice sends photons, Bob measures them, and together they generate a messy first draft of a key. Sifting removes the cases where they use different bases, leaving them with a shared, raw key. Next comes error correction, where they clean up any mismatches and make their bits perfectly align. But even after that step, Eve might still know something. So, BB84 finishes with privacy amplification. This is where Alice and Bob compress the key using a shared hash function. That single move destroys any partial information Eve could have gained earlier. The key becomes shorter, but dramatically more secure. And when all three steps are complete, sifting, error correction, and privacy amplification, Alice and Bob finally share a provably secure secret key. This is the entire BB84 post-processing pipeline, start to finish. So here's the big picture. BB84 doesn't end when Alice sends photons to Bob. The protocol relies on a series of post-processing steps that turn noisy quantum measurements into a real, usable secret key. Sifting removes all of the basis mismatches and gives Alice and Bob a shared, raw key. Error correction cleans that key up and makes their bits identical, without revealing them. But even then, Eve might still know something from earlier in the exchange. That's why privacy amplification is essential. By compressing the key with a shared hash function, Alice and Bob wipe out any partial information Eve could have gained. The final key is shorter, but it's exponentially more secure. And when you put all of these pieces together, sifting, error correction, and privacy amplification, you get the full BB84 post-processing pipeline. This is what transforms BB84 from a physics demonstration into a rock-solid cryptographic protocol. Thanks for watching. I hope this breakdown of BB84, error correction, and privacy amplification helped you see how the protocol really works behind the scenes. If you enjoyed the video, make sure to like and subscribe. It really helps the channel grow, and it lets us keep producing deep-dive quantum security content like this. Visit spectreai.ai for hands-on labs in quantum security. Check out our books on Amazon if you want to go even further. And drop a comment below to tell us what you want to learn next. Thanks again for being here, and I'll see you in the next video.